Hello everyone, welcome to this live problem solving session for the course on traffic engineering. I am Sethi Vinayaga, PhD scholar in the Department of Civil Engineering at IIT Madras. We have completed all the 12 weeks of content for this course already. So this session is an extra session aimed at summarizing all that we have seen so far in the course. Okay, so it will be so we'll try to look at questions from all the different concepts that we have seen over the 12 weeks, okay, and related problems to those concepts. Okay, so let's get a quick overview of what was covered in this course. Okay, so we had 12 weeks as I was mentioning earlier. So initially the first week we were looking at a basic introduction to what traffic engineering is, right? So we were looking at what are the different traffic components and what are their characteristics, right? So the basic components is, so we have so in traffic engineering we are mainly concerned with road traffic, right? So which so the system contains, so the infrastructure, so which includes the roads as well as uh, the traffic control devices, right? And then we have the road users, and this could be both drivers, passengers, as well as pedestrians and cyclists, right? So whoever is using the facility. And then you'll have traffic operators, right? So who does the monitoring and operation of say the traffic control devices, or the public transit operators, and so on, right? So all these components together make up the traffic system, right? And so this interaction between all these components makes up the traffic system, and that's what we are trying to study in this course. So in the second week we were looking at traffic stream parameters and the basic relationships between them. So when it comes to traffic stream parameters, so there are two major categories. Uh, so one is the macroscopic parameters, the other is microscopic parameters. Right. So under macroscopic parameters, where we have flow, speed, and density. Under microscopic, so this speed is actually the stream speed, not an individual vehicle, but the speed of the stream as a whole. When it comes to microscopic parameters, we look at spacing, or the distance headway, then time headway. We can also look at speed of individual vehicles, right? So macroscopic parameters, so these are concerned with the stream as a whole. Okay, we are describing, you use these parameters to describe the stream as a whole, traffic stream as a whole, whereas the microscopic parameters, these are concerned with individual or a pair of vehicles, right? So this is at a smaller scale, that's why it's called microscopic, whereas the stream is at a and it's like an overview of the whole traffic system, so it's a macroscopic parameter. Okay, and then we will look at the relationships, right? So some basic relationship in the macroscopic scale is Q, which is used for flow, is equal to kV, right? So K is here density, and V is here speed, right? So this is the basic relationship that we have. And then we also have relationship between these um, parameters, like for example density can be derived from density can be derived from the spacing, right? So it is inversely proportional to your spacing. Let's say spacing is S. Okay, so if your spacings become smaller, right, so your density will become higher, right? Similarly, flow will be inversely related to time headway. Let's call time headway as t, right? So if time, what is time headway? Time headway is the time gap between two consecutive vehicles to cross a given point, right? So if the time headway is large, it means that the gap between the pair of vehicles is higher, right? So if time headway grows larger, your flow will come, right? So that there is an inverse relationship between these parameters. So these are the relationship that we were looking at, and then week two we were also looking at EA procedure. So what is EA procedure? EA stands for environmental impact assessment, right? So this is very important because you know road traffic is one of the major contributors to the air pollution, right? So when you look at all the different modes of transport, road transport is one of the highest contributors, right? So there is a need to take care of the environmental health when we are working with the transport projects, right? So AA procedure helps us to assess how much of an impact that a given road project or a road system has on the surrounding environment, right? So we were looking at that in week two. In week three, we were introduced to the concept of shockwave and queuing, right? So what is shockwave? So this is a method for analyzing the traffic stream, okay? Okay, so in shockwaves, so basically what happens, so when two different traffic states meet, how does this traffic state propagate along both space and time? So that's what a shockwave the shockwave method helps us determine, right? So basically it is a propagation of the shockwave is nothing but propagation of uh, traffic state, say boundary along space and time, right? How the boundary between two different traffic states moves along the space and time. So that's what the shockwave tells us, right? Basically shockwave is the boundary that separates the two traffic states. So and queuing, so because of different factors, queues will be formed, right? So for example, if you take an intersection, signalized intersection, so when the signal turns red, so vehicles have to stop at the intersection, right? So and during this period, we can still have vehicles coming into the intersection. So because of this, because inflow is positive and the outflow is zero, so the vehicles have to stop, and then the queue builds up, right? So how do we analyze such queues? So those were covered in week three, and in week 4 and 5, so we were looking at capacity and level of service analysis, right? So using different methods. So one, first we started with the US highway capacity manual, and then we were also looking at the Indian HCM manual. It's called Indo HCM. So we were looking at how to analyze this for freeways, multi-lane highways, two-lane highways, then urban street segments, right? So using both the manual, so we are looking at how to do the capacity and loss analysis for all these different types of facilities. Then for the next 3 weeks, weeks 6, 7, and 8, we were looking at traffic control at intersection, right? So because at intersections you have conflicting traffic movements taking place, so there is a potential for crashes and accidents. So traffic control devices or methods need to be implemented so that these conflicting movements are safely allowed to pass through the intersection. Okay, so within that, so we are looking at three different levels of traffic control: level 1, level 2, and then level 3, right? So each with increasing complexity, right? So level 1 is where there is no specialized devices that are installed. So basic rules of the road should be followed. Whereas level 3 is the most complicated, so where we'll have like signalized intersections controlling the traffic, right? So we were looking at all these three different levels, and in particular, we were when we are looking at signalized intersection, we were looking at how to design the signals, right, and how to analyze the traffic delay, or how to evaluate a given signal plan. And then moving on to week number 9, so we were going into car following models and traffic simulation, right? So what is a car following model? So basically it is modeling the the longitudinal movement of vehicles, right? So we have two vehicles on the road, right? So the vehicle in the front is called the leader vehicle, and the vehicle that is behind it, it's called the follower vehicle, right? So based on the movement of the leader, how does the follower respond to it, right? So that process is modeled, and those models are called as the car following models, right? So here we were looking at multiple ones, so like the Forbes model, Pipes model, then the General Motors models. So here we had like first generation, Gen 1 up to Gen 5, okay, 5 generations of the GM car following model. So all these were covered, right? So what is the theory behind it, right? And how what are the different parameters that are associated with these ones? And then we are also looking at Wiedmann's car following model. Okay, and then we were also looking at traffic simulation, right? So where we are trying to study the system in a non-intrusive way, right? So we if because traffic systems are very complex, and also changing them in reality to study them is very difficult. So we try to replicate that system using models like the car following models to replicate their behavior, and then make small changes based on our theory, and then try to see what is the effect that is caused. Okay, so that's what we do in the traffic simulation. And then in week number 10, so we are looking at different measures and strategies for traffic control and management, right? So here what the idea is, how to make use of, how to make efficient use of existing facilities. So because the funding, the capital that is required for new infrastructure is higher for traffic systems, and also the space that is available for building new facilities is also limited, right? So we are trying to make optimal use of whatever is the facility that is already available before we try to build any new facilities, right? So what are the measures and techniques that we can employ for achieving that? So that was covered in week number 10. Then in week 11, it was dedicated to purely parking management, right? So how different strategies can be adopted that has an impact not only on the parking efficiency, but also on the traffic demand, right? So here we are looking at what are the different methods of surveying to get to know about what is the existing supply conditions, what is the demand for parking facilities, and then what are the strategies that can affect both the supply and the demand for the parking management. And then the course concluded with week 12, which is focused on traffic safety, right? So here we are looking at what are the like the safe system approach, why traffic safety is very important, right? So all those concepts, and also some of the strategies for reducing accidents. So these were covered, in the traffic safety module. Okay, so that's all that was covered in this course. Okay, so that's the overview of all the things that we have looked at. So now we'll try to cover some problems related to each of these concepts, okay, individually, right? So this is like a refresher or a recap for what we have already seen so far, okay? So let's start with this week's questions. So the first question is, which of the following statements is false with respect to mobility and accessibility? So the options are, both mobility and accessibility of car is more than bus. B, mobility of an arterial road is more than expressways. C, accessibility depends on the proximity of the land to major roads. And D, mobility depends on the effectiveness of through facilities. Okay, so this is from the early concept that we have seen. So the mobility and the accessibility function of different facilities, right? So it varies. Mobility and accessibility varies for different facilities. So if you try to draw a graph like this, so where the y-axis represents mobility and the x-axis represents accessibility, the mobility accessibility function would be something like this, right? So where the freeways, major arterials, minor arterials. So these would be towards the left end of this graph. So where they provide a higher mobility, right? So whereas their accessibility is comparatively smaller, right? So this is followed by the collector roads, the major collector roads, then the minor collector roads, and then you'll have the local streets. Okay, so these facilities provide better accessibility, but they'll have limited mobility, right? So accessibility is basically how easy it is, how easy it is to get to the facility. Mobility is about efficiency of the through movement, right? How fast can you go through that particular facility, to reach your destination. Right, so this is, so based on this mobility accessibility, we can make a hierarchical classification of the facility from freeways to the local streets. Okay, and this is with respect to the facility. Similarly, we also have mobility and accessibility function, which varies by the mode of transport as well, right? So for example, car has higher mobility and accessibility. Why? Because it can provide door-to-door access, right? So you can get out of your house and then take the car and then go right to the door of your the destination that you want to reach, right? So it provides higher mobility and accessibility. So relatively, bus will have lower mobility and accessibility, right? So because to catch the bus, you need to move from your origin location to the bus stop, right, or a bus station. So which maybe you have to put some effort to reach there, right? So it's not as easy as it is like taking your car, right? So therefore it has lower accessibility relatively. Similarly, the mobility also will be lower because in buses you have to buses are typically slower moving than cars, and also you'll have to stop at multiple stops in the middle before you get to your destination, right? So it will take longer to reach your destination. uh, so that's how that there's variability with respect to modes as well as with facility. So keeping that in mind, so if you look at these statements, so first one says that both mobility and accessibility of car is more than bus, so which, as we have seen now, is correct. B, mobility of an arterial road is more than expressways. So this is not correct. So expressways is similar to your freeways, right? So which means that expressway has a higher mobility but lower accessibility when you compare it to arterial, right? So here we are only looking at mobility. So it is higher for expressways than arterial. So this statement is incorrect. C, accessibility depends on the proximity of the land to the major roads. This is true. It's accessibility So if you have closer, if you are located closer to the roads, so you'll be able to get to that road quickly, right? So it will be easier for you to get to that. So accessibility does depend on the proximity. So C is correct. And D, mobility depends on the effectiveness of the through facility. So this is also correct because mobility is dependent on how effectively or how efficiently can you move through a facility, right? So that's by definition, it depends on the effectiveness of the through facility. So D is also a correct statement. So the only incorrect statement is option B. So B is the answer. So question number 2, accept or reject the given statement. A person with a visual acuity of 6 by 6 is said to have poorer vision than a person with a visual acuity of 6 by 8. Okay. So when we are talking about visual acuity, so there we'll always be given two numbers, right? So numerator and a denominator. So the numerator is uh, the distance from which a normal person can see an object. Okay, and denominator is same thing, distance from which the person assessed can see the object. Okay, so your numerator is like your reference value. Okay, so like for a normal person, what is the distance from which what is the distance from which he can see an object, maximum distance, and denominator is what the person who is undergoing this assessment can see. Okay, so if the person who is getting assessed can see the same object from a farther distance, okay, if d is greater than n, so there is a better acuity, right? Right, so um, sorry, actually this is opposite. So the denominator is for the normal person, whereas the numerator is for the uh, so the denominator is for the reference for a normal person. The numerator is for the person who is getting assessed. Okay. So in that case, if denominator is greater than the numerator, what does this mean? So a normal person can see from a farther distance than the person who is getting assessed, right? So which means the person, this person has to get closer to the object in order to see it. So which means this is a poorer visual acuity. If denominator is less than or equal to n, which means the person who is getting assessed, he is able to see the same object from a much farther distance than a normal person, right? Which means the visual acuity is better, right? So if you look at that, so a person with a visual acuity of 6 by 6, so which means that this person has a normal eyesight, right? So because he is able to see from a distance of 6 meters, right? So the normal person is also able to see from a distance of 6 meters, right? So which means that this person is having a normal eyesight. So compared to that, this person who is having 6 by 8, so which means that he has to get much closer, right? So 2 meters closer to the object than a normal person, because a normal person is able to see from a distance of 8 meters, but this person is able to see only from a distance of 6 meters, right? So which means that 6 by 8 is a poorer visual acuity. So 6 by 8 is poorer than 6 by 6, right? But the given statement says the opposite, right? So 6 by 6 is poorer than 6 by 8, so we reject the given statement. Okay, so third question is, which of the following figures are correct regarding the speed, flow, and density relationship? Okay, so we are given with three figures. So one is speed versus density, second is flow versus density, and third is speed versus flow. Okay, so if you look at speed versus density first, right, so here we are given with a monotonically decreasing relationship, right, so and it is linear, right, so so when the density is 0, so we have a highest speed, so this is nothing but the free flow speed, right, and when density is maximum, so this is equal to the jam density kj, so in that case we have, you know, 0 speed, right, so which is correct, right, so when you have lesser density, which means there are fewer vehicles on the road, and therefore the drivers can you know, travel at their desired speed, right, so they can travel at a higher speed as well, so which is your free flow speed. And when you have jam density, that is, you know, all the vehicles will come to a stop, right, so they cannot move, so the speed will be 0, and between these two conditions, so there will be a linear variation in the speed, so this is a correct relationship between the speed and density. uh, Next, we have the flow versus density. So flow versus density is not a monotonic relationship. It's a nonlinear one as given here. So when the flow, when the density is 0, so you do not have enough vehicles on the road, right? So therefore the flow will be smaller, right? So what is flow? Is basically the number of vehicles that are crossing a particular, you know, location on the road in a given period of time, right? So when you have fewer vehicles because the density is small, so your flow will also be smaller, right, so this part is fine. So similarly, when you have very high flow, right, it's close to your jam density, right, so in that case, again, because the vehicles are not able to move, even though you have enough vehicles, but they are not moving quickly, right, so because of that too, the number of vehicles that will cross a point in a given time period will also be smaller, right, so these 2 points are correct. So in between these two, at a particular you know, intermediate density, which is called as a critical density, you will be able to get the maximum flow, right, so therefore this is the correct relationship between the flow and density. So second relationship is also correct. So the third one, speed versus flow, so this relationship is not correct because, so because we can get this third relationship by combining the first and the second ones, right, so what do we know? When density is, you know, 0, so we have the highest speed, right, so we have the free flow speed, and we also have the you know, least flow, right, so 0 flow. So so which means when flow is 0, right, when flow is 0, what happens? So two densities are possible, one is 0, other is kj, right, so which means that when two densities are possible for a given flow, then the two speed values are also possible, right, because at 0 flow the speed is ffs, and at jam density the speed is 0, so which means at 0 flow, 0 speed is also possible. This corresponds to the jam density, and a higher speed equal to the free flow speed is also possible, right? And and the variation between these two would be something like this, right? So as your flow increases, right? So as flow increases, what happens? Density, density will also increase initially from 0. So as density increases, so what happens when density increases? Your speed will come down, right? So from here, so the speed will start coming down with increase in density, and maximum flow is here. So that corresponds to the critical point here, right? Once we have reached the critical point, so what happens? When density increases further, your flow will keep coming down, right? So your flow should keep coming down, right? So but because density speed is you know, linearly related to density, it will still keep reducing, right? So it will keep on decreasing, so it will keep on decreasing and go all the way to 0, right? So this is the correct relationship between the speed and flow. So this is also non-linear, but it will be like this. So out of these three figures, only figure 1 and figure 2 are correct. Third figure is incorrect. So B is the right answer. Okay, next question number 4. We have to calculate the maximum flow in vehicles per hour on the road if the speed flow speed relationship is given as Q is equal to 215 V minus 41 V log V, where V is in kilometers per hour and Q is in vehicles per hour. Okay, so here we are given with flow density, sorry, flow and speed relationship, and we want to find the maximum flow. Okay, so how do we do this? So this is a function, right? So this is the flow function as a flow as a function of the speed, right? So if you want to find the maximum of a function, we have to find the point of inflection, right? So where the slope becomes zero. So we want to differentiate the flow with respect to the speed. Okay, so if this that gives us the slope of this curve. So if we differentiate this, what will we get? We will get 215 because v is the variable with which we are differentiating, minus 41 into, so here we have to use the product rule, so that is v into log v. So first differential of v is just 1, so times log v, plus differential of log v is 1 by v, so v into 1 by v, right? So which means 215 minus 41 into 1 plus log v, right? So this is the slope, right? So we have to equate this to 0, right? So if we equate this to 0, so what will we get? 250 by 41 is equal to 1 plus log v. Okay, so log v is equal to 215 minus 41 by 41, right? So if we solve this, we will get v is equal to 69.68 kilometers per hour. Okay, so this right, so we can also so this is the point, right, at v is equal to 69.68. The slope of this particular curve is 0, right? So this could belong to either the minimum or the maximum of this function, right? So to confirm that, we should find the second derivative, d square q by dv square, right? And then look what is the value at 69.68, right? So if it is less than 0, then it means that point corresponds to the maximum, right? So you can check that. So for this one, I'm not going to do it. So you can check that in your free time. So it will be negative, right? So this point corresponds to the maximum of this function. So, but we have to find what is the maximum value, right? So we have to substitute this point in the original function. So we have to find q of 69.68, right? So that is 215 into 69.68 minus 41 into 69.68 into log of 69.68. So if we solve that, what will we get? We'll get approximately 2857 vehicles per hour, right? So that will be the maximum flow that we can get for this particular relationship. The right answer is 2857 vehicles per hour. Okay, so the next question is, if the observed time headway in a one-way uh, homogeneous traffic stream is 12 seconds, then which of the following describes the relationship between space mean speed, which is v in kmph, and distance headway h in meters? Okay, so here we want to find a relationship between the space mean speed and the spacing or the distance headway. Okay, so if you recall in the macroscopic traffic flow relationship, q is equal to kv. So the speed that we use v is the space mean speed. Okay, so we want to relate that space mean speed to the distance headway, and what we know is the time headway is 12 seconds, right? So we have to use that information to get this. So if we recall from the overview that we were discussing, so we related the macroscopic traffic flow parameter to the microscopic parameter, and we saw this that q is inversely proportional to the time headway, right? So here the time headway is 12 seconds. Okay, so then what is flow? Flow is actually 3600 divided by 12, right? So because we are using time in seconds, so we are dividing 3600. So in 1 hour is converted into seconds, 3600 seconds, so that we will get the flow in hours. So this will give us a flow of 300 vehicles per hour. Okay, so we can derive the flow from the time headway. Now somehow we have to relate these space mean speed and the distance headway. So distance headway, where can we use? We can use the distance headway with density. So density will be 1 over h, right? So but because here headway is in meters, right? So we can take 1000 by h, okay, 1000 meters for 1 kilometer. So that will give us the density in per kilometer, right? And we know that q is equal to kV, okay? So q is 300, k 1000 by h, and v, right? So we have somehow brought the two parameters that we want into the equation, right? So v and h, right? So everything else is known, only v and h are unknown. So what can we do here? So v is equal to 300 by 1000 into h, so it's just nothing but 0.3 h, right? So v is equal to 0.3 h is the relationship between the space mean speed and the distance headway for this particular traffic stream. So right answer is option B, v is equal to 0.3 h. Okay, next question number 6. You have to accept or reject the given statement. So the statement is both space headway and time headway are microscopic traffic stream parameters. So we have to accept or reject it. So what is the microscopic traffic stream parameter? So as we said, we have traffic parameters, macroscopic and microscopic. So macroscopic means it is related to the stream, right? Microscopic means individual or pair of vehicles, right? So it depends on individual vehicles or a pair of individual consecutive vehicles, right? So space headway and time headway both are defined for a pair of vehicles, consecutive vehicles, right? So if you look at a traffic stream, so let's say we have these three vehicles, so 1 2 1 3, right? So if we take the space headway, it is what the corresponding points, right? So between the two vehicles, so like the front bumper to the front bumper, so this would be h1, and similarly this distance would be h2, right? So h1 need not be equal to h2, right? So it depends on the pair of vehicles. For 1 and 2, the space headway is h1. For 2 and 3, it is h2. Similarly, we will have time headway of t1 and t2 between these pair of vehicles, right? So it is dependent on the vehicles that we are looking at, right? So it's not constant for the whole traffic stream. So such parameters are microscopic traffic stream parameters. So both space headway and time headway are microscopic parameters, right? So we accept the given statement. So right answer is A. Next, question number 7. The projected AADT of a proposed facility is 31,000 vehicles per day. If the proportion of AADT in the design hour is 12% and the peak hour directional distribution is 63:37, estimate the directional design hourly volume DDHV. So what is AADT? So AADT is nothing but annual average daily traffic, right? So which means it is a volume or flow for a given day, right? So it's an average flow for a given day at a particular facility. Here, the thing we need to know is this is not the direction is not considered when this AADT is measured, right? So both directions of traffic flow are included in this AADT, right? So both directions of traffic is counted when we are measuring the AADT. So that is one point that we have to keep in mind. And second point is it is a daily traffic, right? It's for the whole day, not for any particular hour of the day. Okay. So here what we want to find is we want to find the DDHV. So what is DDHV? So as opposed to AADT, it is for the directional design hourly volume, which means it is for a particular direction, right? So for a particular direction. And which direction? That is the design direction. Which is the design direction? Design direction is equal to the peak direction. So whichever direction is carrying the highest flow, right? So that is the direction that we design for, because that is the critical direction, right? So it is carrying the highest flow. So if we take care of that, the other direction will be also fine. So we want to find for a particular direction. And also second is, this is a for a hourly volume, right? So we want to find it for the peak hour, not for the whole day, right? So that is the difference from the AADT to the DDHV. So from a daily, traffic, which does not differentiate between the two directions, we want to convert it into for the volume. We want to find the volume for the design direction during the peak hour, right? So that's what we want to derive. Okay. So here ADT is 31,000 vehicles per day, and what is given to us is during the design hour, right? So the proportion of ADT would be 12%. So 12% of this 31,000 vehicles, which is traveling in the whole day, will be traveling during the design hour, right? And out of this 12%, 63% will go in the peak direction, and 37% will go in the opposite direction. Okay, so that's the information that is given to us. So DDHV can be calculated like this. So DDHV would be AADT into this directional distribution factor, which is the 63%, into the peak hour, the proportion of traffic in the design hour, right? So let's call that K, right? So K is 12% and D is 63%. Okay. So which means DDHV will be 31,000 into 63%, 0.63 into 12%, 0.12. So how much will that be? Two, three, four vehicles per hour, right? So approximately. Okay, so this is the directional design hourly volume derived from the projected AADT. Right, so 2344 vehicles per hour is what is expected, and we design a facility for this volume. So this is the peak demand, in any particular hour that we expect. Question number 8 is, suppose a detector records an occupancy of 0.35 for 15-minute analysis period, and if the average length of a vehicle is 4.5 meters and the detector is 107 centimeters long, then what is the density? Okay, so here we want to find the density from occupancy. Okay, so using occupancy, measuring occupancy is much easier than measuring directly the density from the field. Okay. So occupancy can be measured using like loop detectors, right? So which is giving you the proportion of time, right? So the detector was occupied, a vehicle was within that detector area, right? So in the analysis period, right? So that's what the occupancy gives us, right? So 0.35 means 35% of the time some vehicle was within the detector, right? So that's what the occupancy tells us. So our analysis period is 15 minutes. Out of this 15 minutes, for 35% of the time, the vehicle was occupied in the detector. And the length of the vehicle can be taken as 4.5 meters on an average, right? And the length of the detector itself is 107 centimeters, right? So we want to derive the density from this information. So the relationship between occupancy and density is occupancy by the length of the detector plus the average length of the vehicle. Okay, so if we know these three values, we can estimate what the density is for that corresponding road section. So here we know all this information. So O occupancy is 0.35. This is our O. This is our LD. This is our LV, length of the vehicle. This is our LD. They are in different units. So let's bring them all into one unit, into meters. So this would be equal to 1.07 meters, right? So occupancy doesn't have any units, 0.35 divided by 4. So LD is okay, 1.07 plus 4.5. Okay, so let's find out what that is. So 0.35 by 1.07 plus 4.5, that is 0.0628. Okay, so this is what density in vehicles per meter, right? So because our detector length and vehicle length are in meters, so the unit for this is vehicles per meter, but usually we represent it in vehicles per kilometer. So we have to multiply this by 1000. So it will be 62.8 vehicles per kilometer, right? So I'm just multiplying it by 1000, right? So to convert it from per kilometer to per meter, right? So that is the estimate of the density from the measured occupancy. Okay, so that is 62.84 vehicles per kilometer per lane, because this detector is fixed on only a single lane. So this is for one lane. So if you have multiple lanes, so you can just multiply it by the number of lanes if you don't have individual occupancy values for each lane. Okay, moving on to question number 9. The following speed density relationship is found for a highway segment. So V is equal to 0.001 times K minus 200 squared minus 1.5, where V is the speed in kilometers per hour and K is the density in vehicles per kilometer. So estimate the following. So we want to get what is the free flow speed, what is the jam density, what is the speed and density at the maximum flow, and what is the lane capacity. Okay. So first we want to find free flow speed. So as we saw the speed density relationship earlier, so how was it? It was like this, right? So this was speed and density. So free flow speed is here. So free flow speed is achieved when density is 0, right? So which means that we can find the free flow speed by substituting K is equal to 0 in the given relationship. So V FFS is equal to 0.001 times 0 minus 200 squared minus 1.5. So how much is that? 0.001 times 200 squared minus 1.5. So that would be 38.5 kilometers per hour, right? So that is your free flow speed. Okay, next we want to find what the jam density is. Similarly, from the same diagram, so jam density is where velocity or the speed is 0, right? So we can substitute V equal to 0 now to find the jam density Kj. So 0 is equal to 0.001 into Kj minus 200 squared minus 1.5. Okay, so 1.5 by 0.001 square root of this plus 200 is equal to Kj. Okay, so we can solve this. So square root of 1.5 by 0.001 . So that is about 238.73 vehicles per kilometer. So we can say it is around 239 vehicles per kilometer. Okay, so that is your jam density. Okay, next we want to find out what is the speed and density at maximum flow, right? So for speed and density at maximum flow, so we want to we want to bring the flow into this relationship, right? So far we only have speed and density, right? So we want to bring in the flow into this relationship. So how can we do that? What we know is flow is related to speed and density like this. Q is equal to kV, right? So if you multiply both sides by k, so what will we get? We'll get kV is equal to 0.001 k into k minus 200 squared minus 1.5 k, right? So and this kV will become q, right? So then we can just find the maximum, maximize this function of q, right? And then find what the density is corresponding to that maximum flow. And once we get the density corresponding to maximum flow, we can substitute it back into this equation to get the corresponding speed. Okay, so that's what we are going to do. So if we do this, so first let's expand this 0.001 k into k minus 200 squared. So k squared plus 200 squared minus 400k minus 1.5k. Okay, so that would be so 0.001 k cube plus 40k minus 0.4 k squared minus 1.5 k. So that is 0.001 k cubed plus 40 minus 1.4 plus 38.5 k minus 0.4 k squared. So this is your function q. Okay, so now we want to find dq by dk. So what will dq by dk be? It will be 0.002 k squared minus 0.8 k plus 38.5. Okay, so if we equate that to 0 and then solve for this, so this one equal to 0. Okay, so let's solve that. So what would be k? Minus b Okay, so we'll get two roots for this. So 0.8 plus or minus 0.576 by 0.004. So 0.8 plus 1 is 344. Okay, one root. So the other root is 56. Okay, so we have two values of density here. So if you plot or if you find the second derivative, you'll find that, so this is the point where your density will be maximum, right? So when k is equal to 56, I'm not doing that, so we can again verify that by finding the second derivative, d squared q by dk squared. So that would be, or let's do it, it will be 0.004 k minus 0.8, right? So for the first one, 344, what it will be, 0.004 into 344 minus 0.8. So it will be the second, so d square by dq for 344 it will be 0.576. For 56 it will be 0.004 into 56 minus 0.8, so that is minus 0.576, right? So which means that at 56 the second derivative is negative. For 344 second derivative is positive. Because we want to maximize q, so we will be picking this particular value where the second derivative becomes negative. So 56 is where the flow is maximum, right? So maximum density is 56. Okay, what is the speed corresponding to this? For that we can make use of this equation, right? So here that speed would be 0.001 into 56 minus 200 squared minus 1.5. So that will be 0.001 into 56 minus 200 squared minus 1.5. That is 19.236. Okay, so kilometers per hour. So this is the speed corresponding to the maximum flow, right? So because speed and density have a monotonic relationship, so we can directly substitute the maximum density corresponding to maximum flow and get the speed as well, right? So that is for speed. So then we have to find lane capacity. Lane capacity is nothing but the maximum flow value. So how can we get the maximum flow value? We know the density corresponding to the maximum flow, which is 56. That can be substituted into the flow equation. Okay, so that will give us the maximum flow. So q max will be 0.001 into 56 cubed minus 0.4 into 56 squared plus 38.5 into 56. Okay, so that is the maximum flow. So 0.001 into 56 cubed minus 0.4 into 56 squared plus 38.5 times 56, so that is 1077.216, approximately 1078 vehicles per hour. Okay, so that is the maximum flow. The next question number 10. So here we are given with a shockwave diagram. Okay, so we have different traffic states that are interacting with each other. So we have traffic state A, D, C, A, and B. Okay, so and this is a signalized intersection. Okay, we have a traffic signal here. Okay, so there is a red duration. So during the red duration, vehicles cannot stop, so cannot move. So B is nothing but your traffic state corresponding to jam density. So which means D is free flow condition, right? So there is zero flow. So A is your inflow. During A is your inflow, which is, let us say, it is at a uncongested regime, and C will be your saturation flow. Okay, so these traffic states are interacting with each other. So we want to identify what kind of shock waves are formed between states BA. Okay, so here this is the shock wave. Okay, so this is the BA shock wave. Okay, so BA shock wave. So it is so the slope of this shock wave is negative, right? So if the slope is negative, it is a backward moving shock wave. Okay, so it's a backward one. So we want to find whether it's a backward forming or a backward recovery, right? So here what happens? So as the as the shock propagates farther back, so what happens? The q becomes larger and larger. So the q is nothing but q length is nothing but the vertical distance between from the signal to the shock wave. Okay, so that gives you the q length. Okay, so what we see is that the q keeps growing, right? So this shock wave keeps increasing the q. So this is a backward forming shock wave, right? So because the q is forming because of this shock wave, so BA is a backward forming shock wave. So next is B and C. So that is this part. So what happens is this is also having a negative slope, right? So as we see, this is a negative slope. It is moving back. So this is also a backward moving shock. So this is a backward moving shock. But again, we have to decide whether it's a backward forming or a backward recovery. So what happens with this shock wave? What we see is that the Q length keeps decreasing, right? So the distance between this C shock wave and the BA shock wave, the vertical distance, that is the Q length, which becomes smaller and smaller, right? So as it moves back. So which means that this is a backward recovery shock wave, right? So because the Q length is reducing. And the third one is BD. So it is this particular shock wave. So what we see is the slope of this is slope of this shock wave is 0. So which means that this is a stationary shock, right? So stationary shock, and whether it is a forward or a backward stationary shock. So it is forward. So because it is before the signal. So forward stationary would be, so the congested one will be below, right? So the congested state will be below, and the free state or the free flow state will be above the shock wave. So if that is the case, it will be a forward stationary shock wave. So here we have a congested state behind. So this is a frontal stationary shock wave. Okay. So BA is backward forming. Okay. BC is backward recovery, and BD is a frontal stationary. So the right answer is option D. Okay, then question number 11. So accept or reject the given statement. So the statement is, when traffic demand exceeds the capacity, observed flow equals the demand. So we have to accept or reject it. So what happens is, so when you have flow or demand is greater than capacity, right? So what happens? So the maximum number of vehicles that can pass through right your section would be capacity, right? So that capacity is the maximum value, right? So you cannot observe vehicles more than the capacity value, right? So what happens? So because there is enough demand, right? So the flow that you will see would be equal to the capacity. So this is what you observe. Q is what we are observing. Okay, and Q cannot be greater than the capacity, right? So because of this higher demand, excess demand, more than the capacity. So what we will be observing in the field is this, right? So but in reality, this is the condition: demand is higher. Right. So in the other case, when demand is less than capacity, so what happens? So greater than or equal to. So when demand is less than capacity, Q would be equal to the demand. Okay. So what happens? So when there is not enough demand, right? So when compared to the capacity, so whatever we are observing is equal to what is the actual demand. So observed flow is equal to actual demand in the case where demand is not exceeding capacity. But when demand exceeds capacity, what we are observing is lesser than what the actual demand is. Okay, right? So therefore, the given statement that when traffic demand exceeds capacity, which is this condition, observed flow equals the demand, is incorrect. Right? So we reject it. Observed flow will equal the capacity, which is lesser than the demand. Okay, question 12. So we are given with the following values of PTSF and ATS. What is PTSF? PTSF is percent time spent following, right? And ATS is average travel speed. Right? So these are the performance measures that we use for determining the LOS of two-lane highways, right? So two-lane highways. So we have given with 4 road segments 1, 2, 3, and 4, and the PTSF values and ATS values for these 4 segments. So you want to determine the LOS first, assuming that these segments belong to a class 1 2-lane highway, and second, assuming that they belong to a class 2 highway, right? So for class 1 highways, so we use 2 performance measures. So one is the ATS and PTSF, but if it is a class 2 highway, you only use one measure, which is the PTSF value. Okay. So first let's assume that it's a class 1 segment, okay, and then find what is the LOS value. Okay, so first looking at segment 1, so ATS is 54, so 54 means it is coming in LOS B, okay, and PTSF is 36, so which is also coming in LOS B. So overall class segment 1 is LOS B. So next for segment 2, ATS is 47, so 47 is LOSC, and PTSF is 54, which is also in the range 50 to 65, so that is also LOSC. So segment 2 is LOSC. Segment 3, ATS 42, which is LOSD, and PTSF 72, which is also corresponding to LOSD. So segment 3 is corresponding to LOSD. And segment 4, ATS is 30, which is less than or equal to 40, so LOSE, and PTSF is 90, which is greater than 80, so that is also giving us LOSE. So overall, segment 4 is also LOSE. So this is assuming that these segments are in a class 1 highway. So if it is class 2, so we should only look at the PTSF values and use these categories. Okay. So first PTSF is 36. So 36 is less than or equal to 40. So it is belonging to LOSA segment 1. And segment 2 PTSF is 54. So 54 is between 40 and 55. So that is LOSB. Then we have 72 for segment 3. 72 is corresponding to LOSD. And then 30, uh, 90. 90 is greater than 85. So which is corresponding to LOSD. Okay, so we have BCDE for class 1 and ABDE for class 2. Okay. Next, question number 13 is, when a facility is operating at or near its capacity, what will be its level of service? So options are LOSA, LOSC, LOSF, and LOSE. Okay, so here, so LOSA is the best LOS that you can get, and you have up to LOSF, so which is corresponding to the worst condition, right? So LOSA, this is like free flow conditions. LOSF is the breakdown condition where your demand exceeds the capacity. Okay, so in the middle you have like LOSC. LOSC is, where there will be local deterioration to service quality. Even though you will not see the whole traffic stream, getting affected, so, but there will be local deteriorations in the service quality. And just before breakdown, so breakdown is when demand exceeding capacity. So just before it exceeds, it will be near the capacity, right? It will be close to the capacity. So that is where we have LOSC, right? So demand is approximately equal to the capacity. That is your LOSE state. So therefore, the right answer is option D. It is LOSE. Okay, question 14 is, which of the following are the performance measures for determining the LOS of urban street segments? The options are density, travel speed, volume to capacity ratio, and percentage time spent following. Okay, so for different roadway facilities, we use different performance measures. So density is used for freeway and multi-lane highway. The percentage time spent following is used for two-lane highways, especially class 1 and class 2. Right? For urban street segments, we use two performance measures. So they are the travel speed and volume to capacity ratio. So these two are used for urban street segments. Right? So travel speed is like a measure of the delay that is experienced by using the facility, whereas the volume to capacity ratio is a measure of the through movement efficiency. Right? So these two measures are used together when the LOS is determined for a urban street segment. So the right answer is option B and option C. Okay, question number 15 is which of the following statements is correct with respect to level 1 control at an intersection? So the options are sufficient sight distance is not essential for safe operation. Traffic signal is an example of level 1 control. The driver is expected to obey the basic rules of the road, such as the right of way rule, and D is all of these. Okay, so we have looked at three levels of traffic control: level 1, level 2, and level 3. Right, so level 1 is the basic traffic control, right? So where the drivers have to obey the basic rules of the road. Okay, so level 3 is like signals. So when we have control using traffic signals. It's sufficient side distance is not essential for safe operation. This is not correct. Sufficient side distance is required, right? So for any intersection, so sufficient side distance must be provided. So so even for level 1 intersection, so that should be there. So option A is not correct. Option B, traffic signal is an example of level 1 control, wrong, because it is a level 3 control. And C, the driver is expected to obey the basic rules of the road, such as the right of way rule. So this is applicable for level 1 intersection, right? So that's what is the level 1 control does. The basic rules of the road is what is being exercised in such situations. So C is the right answer, and all of these is not correct because first two are incorrect. So the right answer is option C. Okay, then question number 16. The capacity of a lane group of signalized intersection is 625 through passenger cars per hour. The duration of each analysis period is taken as 15 minutes. The demand flow rate for the lane group during each 15-minute interval is as given below. So we are given this table. Estimate the length of the queue in TPC at the end of 60 minutes. Assume there is no initial queue at the beginning of the first 15-minute interval. Okay, so here we want to find the queue length, right? So what we are given with is the demand in each 15-minute period at a signalized intersection. So how do we do this? So for each period, we want to calculate this value. Okay, let's go to the new page. So here we have 4 analysis period. Right, so that is period 1, period 2, 3, and 4. And the duration of each period in hours is 1/4 of an hour, 0.25. Okay, so what we know is the demand is given to us. So the demand is in TPC per hour through passenger car. So 645, 637, 649, and 657. So the capacity for the lane of the intersection is constant, right? Capacity will not change. So in the same unit, it is 625. This is not going to change across the period. So what happens? So whenever the demand is higher than the capacity, you are going to face increasing queue length, right? So because that particular intersection is able to serve only 625 vehicles, right? So but if more vehicles are coming, so those excess vehicles will have to wait, right? So they will form a queue. So the queue length will increase when when V is greater than C, and when V is lesser than C, right? So if there is any queue that is present, so that can be served in that analysis period, right? So the queue length will decrease when V is less than C, right? So that's what we are trying to do. So we'll find two quantities, QB and QE. So QB is what is the queue length at the beginning of the analysis period. So what we are assuming is at the start of our analysis there is no queue, so QB is 0 for the first period, right? So how do we find the QE? The queue at the end of the period is nothing but whatever is the initial queue, right? So this initial queue is either going to go high or go down, right? So V minus C is the rate at which the queue will the queue length will change. Okay, so V minus C, if it is positive, which means that the queue length will increase. If V minus C is negative, the queue length will decrease, and this is for a given hour, right? So V and C are hourly values, so hourly flows. So we have to multiply it by the corresponding analysis period duration, so to get the particular change in the queue length, right? So this will give us the queue length at the end of the analysis period. So for the first period, it will be what? Initial, at the beginning, there is 0q plus what is v minus c? It is 645 minus 625 into 0.25. So it is 0 plus 20 into 0.25. So it is 5. So there will be a queue of 5 vehicles at the end of the first 15 minutes, right? So, and whatever is the end of the first period will become the beginning of the next period. Okay, so there will be 5 vehicles at the beginning of the second 15-minute period. Okay, so with that we have to do the same calculation. So for that, it will be same thing you do. So QE would be 5 plus 637 minus 625 into 0.25, right? So that will give you 8. Okay, so there will be 8 vehicles at the end of the second period and so on. So this 8 vehicles will be at the beginning of the third period. And similarly, if you repeat this, you will find that there will be 14 vehicles at the end of the third period. Then finally 22 at the end of the fourth period. Why? The queue length keeps on increasing because the volume or demand is consistently higher than the capacity in all the 4 periods. So the queue length keeps on increasing throughout our analysis period. So finally, we will be seeing 22 vehicles in queue at the end of the 1 hour period, right? So that's why the right answer is 22 vehicles. Okay, next question is, as per the planning level analysis for an intersection, absence of protected phase for right turning vehicles is justified if there is more than one right turn lane on the approach. So we have to accept or reject this statement. Okay, so when we look at planning level analysis, actually there are 3 criteria, which if the criteria is satisfied, we have to provide a separate phase, which is the protected phase for the right turning vehicles. Okay, so any one of the 3 criteria, if they are if it is met, we have to provide the protected phase. So the first criteria or condition is that if the volume of the right turning traffic VRT is more than 240 vehicles per hour, right? So more than 240 vehicles per hour want to turn right, right? So in that condition, we must provide a protected right turn phase. The second condition is it's a combination of the right turning traffic and the opposing traffic. So if the volume of the right turning traffic multiplied by the volume of opposing traffic is more than 50,000, right? So then in that case, we must provide a right turning phase, protected right turning phase. So this is for condition where you have 2 lanes, right? So if you have 3 or more lanes, in that case, this right side will become 110,000, right? So this is dependent on the number of lanes that are present. So that is for condition 2. The third condition is depending on the number of right turning lanes. So if there is more than one right turning lane, so then also we have to provide a protected phase for the right turning movement. So here, it says the absence of a protected right turning vehicles is justified if there is more than one right turn lane. So this is incorrect, right? So when there is more than one right turn lane, we must provide a protected phase for right turn. So the absence of a protected right turning phase cannot be justified by this, right? So therefore we reject the given statement. Okay, next question number 18. The two-way total peak hour traffic volume between two intersections, which are 920 meters apart, is 4250 vehicles per hour. Which of the following statements is correct with respect to the variant model of the coupling index? Okay, so here CI refers to the coupling index or the variant of the coupling index. Okay, so how do we get this coupling index? So CI variant. So variant equal to V square, V divided by D square. So V is thousands of vehicles per hour, right? So the volume is expressed in thousands of vehicles per hour, and D is your the distance between the intersection. Okay, so distance in miles. Okay, So we know what V is. V is 4250 and the distance is 920 meters. So we have to convert that into miles. So 920 meters is equal to 0.57 miles. Okay, so this is what we have to use. So V is 4250 by 1000, right? So because we want to express this in terms of thousands of vehicles per hour. So that is 4.25 thousand vehicles per hour. Okay. So the CI value is 4.25 by 0.57 squared. So that comes out to be 13. Okay. So with this, we'll have to look at what the different options are. So we know the value of CI is 13, right? So C and D cannot be true. Okay, we can directly eliminate it. So looking at A and B, where the value of CA is 13. So A says, therefore, signal coordination between the intersections can be considered. B says, signal coordination between the intersection is desirable. Okay. So for the variant model, there are three cases that are possible where CA is less than 1, CA is between 1 to 50, and CA is greater than 50. Okay. So when CA is greater than less than 1, no coordination is required. When it is between 1 and 50, coordination can be considered. When it is greater than 50, then coordination is desirable. And so this is according to the variant of the CA model. Okay. So here, since we have the value of CA is 13, so it falls in 1 to 50 range. So coordination can be considered. Okay. So therefore, option A is the right one for this. Okay, question number 19. For an actuated signal, presence detection with a 95-foot detection length is used on an intersection approach. The front edge of the detector rests on the stop line. Assume a head-to-head spacing between vehicles in queue is equal to 20 feet. Startup loss time is 3 seconds. Saturation headway is 2 seconds. Estimate the value of G min high in seconds. Okay, here we are looking at um, the signal design where we have an actuated signal. Okay, so with the 95-foot detector being used. Okay, so what we will do is we will assume so because we are estimating the high range of the Gmin, so we'll assume that the entire detection area is filled with the vehicle queue. Okay, so if entire detection area is filled with the vehicle queue, so we have to find how many vehicles are there in the detection areas, right? So how do we do that? So we can make use of the head-to-head spacing. So we assume that because the vehicles are packed together in the detection area, so using that we can estimate how many vehicles are there in the detection area, and then what is the time required for clearing all these vehicles. So that will give us the minimum amount of green time that is required. Okay, so how will we find the number of vehicles in queue? So the detection length is 95 feet. Okay, and the head-to-head spacing is 20 feet. Okay, so we have to round this value to the higher end. Okay, so if we round it up, so what we will get is there will be 5 vehicles in the queue. So this is the maximum number of vehicles that we can assume to be in the queue, for finding the minimum green time. Right? Once this is there, so what we need next? So what is the time required to clear this vehicle? So whenever the signal turns green, okay, so we know that some amount of time is lost, right? So the initial vehicles will take little extra time over the saturation headway to cross the intersection, right? So to cross the stop line, right? So that the sum of those extra times for those first few vehicles, so that is the startup loss time. Okay, so that is L1. So that we should definitely give, right? So irrespective of how many vehicles are there, the startup loss time should be included. So then for the number of vehicles that are there, so each vehicle we can then assume to take a time equal to the saturation headway for crossing the intersection. Okay, so the startup loss time is 3 seconds. The number of vehicles is 5 and each vehicle will take 2 seconds to cross. So 13 seconds is the minimum green time that is required for this uh, actuated signal. Okay, so G min high is 13 seconds. Okay, next, accept or reject as per the third generation car following model. So this is with respect to the General Motor models. So the dimension of alpha naught constant in the sensitivity term is meter per second square. So we have to accept or reject it. So if you look at the third generation model, so we have the response, which is acceleration. Okay, so second derivative of the position for the n plus 1, which is the follower. This is the response. So this will be a function of the alpha naught sensitivity term, and this sensitivity term also has the spacing between the vehicles, so which is x n minus x n plus 1. So the spacing is there, and then the stimulus is nothing but the relative speed, right? So x dot n minus x dot plus 1, right? So what happens here? So the response has a unit of meter per second square. Okay, stimulus is in the unit meter per second, and the spacing is having this unit meters, right? So which means that, so finally what we are having is 1 over second, right? So this must be multiplied with the units of alpha naught to get meter per second square. Okay, so what should be alpha naught? So alpha naught should be having the unit of meter per second, so that the dimensions match on both sides of the equation, right? So alpha naught cannot have meter per second square, it must have meter per second in the third generation model. Okay, so which means that the given statement is incorrect, so we are rejecting it. Question 21. As per the General Motor car following model, if the lead vehicle decelerates at time t, the following vehicle at delta t accelerates, decelerates, or no change in the speed of the following vehicle. Okay. So what we saw, the stimulus in the car following model, General Motors car following model, is the relative speed, right, between the leader and the follower, right? So when the lead vehicle decelerates, so what happens? So this is going down, okay, and this is remaining constant, okay, so which means that this whole value is going to be negative, okay. So this value is multiplied by some sensitivity term, okay, so that is a non-negative value. So the response will be negative. The response is nothing but the acceleration or the deceleration of the following vehicle. So if it is negative, which means that the following vehicle will decelerate, right? So a negative value, which comes because of the acceleration of the or increase in speed of the lead vehicle, leads to deceleration, which is leading to a decrease in the speed of the leading vehicle, will lead to a deceleration of the following vehicle after the reaction time delta t, right? So which will lead to deceleration, right? So similarly, if the relative speed becomes positive, right? So in that case, here the response will also be positive, which means the following vehicle will accelerate. And if the relative speed is 0, so which means there is no difference between the speed of the lead vehicle and the following vehicle, then the response will also be 0. The following vehicle will not change its speed. Right? So in this case, when the lead vehicle decelerates, the following vehicle will also decelerate, but not instantly, after a time, which is the reaction time delta t. Question 22. Which of the following statements is incorrect with respect to functional hierarchy, road hierarchy? Option A, mobility is a primary function of the expressways. B, local roads serve to provide access to abutting properties. C, collector roads operates at lower mobility compared to arterial roads. And D, freeways have higher accessibility as compared to arterial roads. So this is same as the hierarchy that we saw earlier in the session. So where we saw expressways and freeways have higher mobility and least accessibility, right? So mobility is the primary function for these facilities. So A is correct. B, local roads serve to provide access to abutting properties. This is also correct. This comes at the other extreme of this hierarchy, where accessibility is higher, where mobility is the least. So which means these roads, local roads, serve as providing access to the neighboring some areas. Okay, so B is also correct. C, collector roads operate at lower mobility compared to arterial roads. This is also correct because collector roads come below the arterials in the hierarchy. So the facilities which are higher in the hierarchy, they have higher mobility and lesser accessibility. And as we go down, accessibility increases and mobility decreases. So because collector road is below arterial, so they also have a lower mobility. So C is also a correct statement. And D, freeways have higher accessibility as compared to arterial roads. So this is incorrect, right? So because freeways are above the hierarchy than arterial roads, right? So they have a higher mobility but lesser accessibility than arterials, right? So therefore D is incorrect. So out of the four, only option D is the incorrect one. So D is the right answer. Question 23 is, which of the following statement is incorrect with respect to employer-based TDM strategies? So TDM stands for traffic demand management. Okay. So here, what are the employer-based TDM strategies? So here, the idea is to reduce the traffic demands. How can we do that? So in particular, the number of vehicles that are on the road. So which options help us do that? So option A, make non-SOV options relatively cheaper. So SOV stands for single occupant vehicle. So non-SOV option means high occupancy vehicles like car share, van pool, carpool, or transit options. Okay, make those non-SOV options relatively cheaper, right? So which means that the people will be incentivized to make use of this non-SOV options. Okay, so that is a correct strategy that we can adopt. So B, offer higher parking rates to carpools and van pools. So what does this do? When the carpool and van pool have a higher parking rate, so that will disincentivize people to use those options, right? So which means they will go back to the single occupant vehicles, so which is not what we want. So B is not a right strategy. C, provision of free or subsidized transit passes. This is good because it will make people choose the transit options because it makes it more attractive because the cost of using that is going to come down. And D, secure workplace parking for bikes. So this is also a right option because bikes here refers to bicycles, right? So non-motorized form of transport. By having a guaranteed place for parking at the workplace, so people will be more willing to bring their bikes because it is they can find the parking for it for sure, right? So that is also a good option for traffic demand management. So these options the employer can provide for their employees, except option B, which is not a strategy that we should adopt. So B is the only incorrect strategy. So the right answer is option B. Okay, then question number 24 is, accept or reject the statement. If the long-term parking demand is less than or equal to off-street parking supply, then the vehicles may be allowed to park to on-street facility. Okay, so with respect to parking demand and the parking facility, so we have long-term demand and we have short-term demand. Okay, so for long-term demand, off-street facility is more suitable, whereas for short-term demand, on-street parking is fine. Okay, so looking with respect to that, so if you look at it, long-term parking demand is lesser than the off-street parking supply. So we have enough, parking supply to cater to all the long-term parking demand, right? So in that case, should vehicles be allowed to park on the on-street facility? No, right? So because long-term parking is more suitable for off-street parking, right? And also the supply is sufficient to cater to all the demand. So in that case, we should not allow the vehicles to park on the on-street facility, right? So that will hamper the traffic on the main street, right? So therefore, this statement is incorrect, right? So in that we should let all the long-term parking be on the off-street supply only, right? So because we have enough supply. Okay, so with that, we are coming to the end of today's session. Right? I hope that this session was helpful. Okay, with this, we are concluding all the live sessions for this traffic engineering course. Okay, so I hope all these sessions have helped you in solving the assignments and also in preparing for the upcoming exam. right? So I thank you all for attending these sessions, right? And we'll see again in some other course in the future. Okay, thank you.